Okay, let's begin. This is the example that was on the board last time. How do we do it?
The integral of from 3 to 0
Give me the general formula. So the length
is equal to the integral from b to
a to b.
a to b,
Yeah,
right?
usually you put the lower one first, yeah.
The square root of the first x prime, so the first derivative squared, plus the first y prime squared. dt.
So, yeah. So here we are going to want from 0 to 3, the radical of, what's this guy, derivative? Technically it is cosh, but let's actually, well, it's 2 times cosh, right? But let's do the basic one, just it's an exponential, so the derivative is that minus that. And so derivative of this is minus 2 squared dt. So we will have, this is going to be e to the 2t minus this times 2 plus e to the minus 2t plus 4. This is going to be e to the 2t plus 2 plus e to the minus 2t. Equals. How do you integrate that?
You can notice that the e to the t minus e to the negative t squared is similar to what you have.
Okay.
But just
So what do we have?
So we would have the integral of 0 to 3 over under the radical e to the t plus e to the negative t squared.
Right, so that's what we have as indicated by, when I expanded this square I got that, and this is very similar to that, except I have a plus sign instead of a minus sign, so that just reminds me, oh, it probably looks the same except the middle sign is changed, and it in fact is. So we have that. So now what is this, the square root of that squared?
E to the t plus e minus to the minus t.
Almost, but not quite.
Minus e to the minus 3.
No, why would you have minus? Square root of x squared is equal to what in general?
Oh, absolutely.
Absolute values. So technically that should be there. In this case, it's not going to matter though, because the exponential is going to be positive. So we have a number that's greater than 0 being added to a number that's greater than 0. It's definitely greater than 0, so the absolute value is actually not going to do anything, and it just becomes that. But it might have mattered, so you should know that it should be there. In this case though, it's not going to matter, because this is always going to be positive, and so now we just integrate each individually. Integral of e to the t is e to the t, integral of e to the minus t is minus e to the minus t, and we have this. So that's going to be e cubed minus e to the minus 3 minus e to the 0 minus e to the 0, so just 0. So yeah, so the length of this curve is e cubed minus e to the minus 3. E cubed minus 1 over e cubed. Okay, so that was it. Just know the formula, and the rest of it is regular integration. Now we want to move on to another topic. 10 point, I believe it's 3. So we're going to introduce something called polar coordinates. So now we want to just talk about a different coordinate system. By the time you get to the end of multi-1, you're going to be able to think in 3 different coordinate systems. Those are very common, and pretty much everyone needs to know those if you're go far enough in science or math. Few people might develop other coordinate systems to help them out with different things. So if you're like a differential geometer or something like that, you might develop some other things. But one important coordinate system is the polar coordinate system. So recall, we currently know something called the rectangular coordinate system. What's the rectangular coordinate system? Well, it's basically how we know to locate coordinates. So, which is all that a coordinate system is, by the way. It's just a way to locate a certain position in a certain space. So we have the familiar xy plane, and if I have a point or a coordinate, I can say talk about 2, 5, for example. Now what that actually means is you would go on the x-axis 2 units, and you would go on the y-axis 5 units, and you kind of match these guys up. And what you notice here is you'll create a rectangle by doing that. We can locate the points by figuring out what is the appropriate rectangle to look at, and we want to take one of the vertices of the rectangle. And so in this case, it's going to be the top right vertex of this rectangle. And so this is how we can locate that point. So if you tell me about the point 2, 5, I know how to find its location. You can tell me about some other point, like 3, 1, and again, I would locate this based on its position relative to some rectangle. I can go over here, 3 units, go over here, 1 unit, create that rectangle, and that's the point. You can give me a point -1, -1, and I can locate that by moving -1. This just tells me, once I put a negative here, it tells me that instead of going to the right, I'm going to go to the left by 1 unit, and instead of going up by 1, I would go down by 1 unit. This gives me what's called a negative, but ultimately, at any given time, you can see visually there's some sort of rectangle in play. So this is called the rectangular coordinate system. Basically how you've been looking at the xy plane your whole life until now. Now we want a new way to look at, we now want a new coordinate system. Not using rectangles, but rather circles. And at this point is the usual aversion to change will kick in. People start wondering, well, why do we need another way to do something? We already know one way to do something. So they're like, oh, you know about exponential functions? Let's talk about logarithms. Why do we need to know another way to talk about exponentials? We already have one way. But it turns out logarithms was pretty useful, right? We learned log differentiation. We can really simplify a lot of calculations by thinking in terms of logarithms. In the same way, by figuring out a different way to locate points in the plane, it turns out that a lot of calculations down the road are going to be simplified. And I'll also mention sometimes some specific situations in which you can do this. So here's how we're going to set up this coordinate system. Suppose we want to locate a point with a radius based on the fact it lies on a circle as opposed to a rectangle. So one way in which you could talk about locating a point in such a way is, okay, I give you some random point out here. What you are going to do is you are going to figure out some circle centered at the origin on which that point lies. You are then going to figure out the radius of such a circle. And then you're going to come up with the two important numbers. Well, you're going to come up with the distance, which is the radius, which we will call r, as well as the angle that you make with the positive x-axis. So, for example, I can locate a point for example, we can locate the point. Now I'm not going to use xy coordinates here, I'm using r comma theta coordinates. And let's say I asked you about the point 1 comma pi over 4. Basically what that means is I am looking at all points that lie at a distance 1 from the origin, which means I have pretty much the unit circle in mind. And I care about one particular angle made with a positive x-axis, namely the angle pi over 4. And if I take the distance from the origin running along that angle and hitting that circle, I will define that coordinate to be 1 comma pi over 4.
It's like physics.
Yes, I was going to bring up that as an example. In physics, you're going to need this. And unfortunately, a lot of times, the math is so important for science, but you learn the math after you already started doing it in science. Yeah. You're going to realize that when you get into multi-2, there are a lot of things you're going to I've been doing this in physics for 2 semesters. Like, why didn't they tell me about this, like, way back then? Yeah. Polar and spherical coordinates that you do in physics, it's based on, well, polar coordinates in physics is based on this. Spherical coordinates is going to be a little different, but you're going to learn about that in multi-1. But yeah, this is just another way to, for those of you not in physics, there's a way to conceive about locations in the plane in terms of circles as opposed to rectangles. We'll talk about why this is useful in a little bit. But yes, it's a big thing in physics. Okay. So I can locate a point like that. So in terms of, instead of thinking in terms of x and y coordinates, I can think of r and theta coordinates. Here are some, so let's actually figure out how this new way of looking at the world is going to work. Some formulas are immediate. So, for example, let's actually figure out, especially how to translate this in terms of the way we've already been looking at the world in terms of this new way. So here's a random point, here's a distance r, here is that. Now, one thing you can automatically start doing is you can throw in your trigonometry. Yes, trig. You're going to need a lot of trig for this section. You can create your right triangle. You will notice that the height of this triangle, that is going to be the y coordinate you're familiar with, and like the base of this triangle, that's going to be the x coordinate that you like. So in terms of translating from a rectangular coordinate system to this kind of coordinate system, a few equations you can immediately get away with. By SOHCAHTOA, you will know that x is going to be r cosine theta, and y is going to be r sine theta. So I can think of the new coordinate system in terms of my old coordinate system using these equations. Also, by the way, you will notice that x squared plus y squared is going to give us r squared, which also kind of tells you right away, I'm thinking of a coordinate that lies on the circle that's centered at the origin with radius r. Now I want it to dawn on you, this is going to be this is going to give a lot of intuition behind some of the forms we're about to derive. But I want you to notice what we just did here. We described the coordinate system. Using parametric equations. Notice what we just did. I just told you what the x-coordinate is doing in terms of some other variable, as well as what the y-coordinate is doing in terms of some other variable. Now, r is sometimes considered a constant, sometimes, but if it's not, you can consider both of these a constant. Probably talk about that pretty soon. But I just described x and y in terms of another variable called theta. And then, what I really had was parametric equations, and that's going to teach us how we can integrate and differentiate and find lengths in polar coordinates, because pretty much exactly what I taught you with parametric equations will take effect here. So that's one thing that you should know. Oh, I should have erased that right away. Another formula that is useful is, again, one from trig. If you look at the tangent of the angle, that can show you what's going on in the x and the y coordinate, because tangent is opposite over adjacent. So that would be, so our new coordinate system which we will call the polar coordinate system. In 3 dimensions, this is called the cylindrical coordinate system. Polar is what we call it in 2D. Is governed by these equations. X equals r cosine theta. Y equals r sine theta. You also have the fact that x squared plus y squared is equal to r squared, and your tangent theta is equal to y over x. You can think of, you don't have to, but you can think of these as being in 2 separate groups, where the first set of equations, this is useful for going from polar to rectangular, right? Which sometimes we need to know how to translate back to our familiar x and y coordinate system. So if someone gives you an r and a theta, you can calculate what the x coordinate of that point will be. And if someone gives you an r and a theta, you can also calculate what the y coordinate of that point will be in terms of the familiar rectangular coordinates. This one is useful for the other way. This set here, going from rectangular to polar. So, if I give you a rectangular coordinate, okay, in the rectangular coordinate system, we're at the point 1, 2. You can plug in 1 here, plug in 2 here, and solve for the r. You can find the r value. And if I tell you, oh, the angle that we are in polar coordinates is pi over 4, you can simply plug in pi over 4 here. You can plug in 1 and 2 here and solve for the theta, and that will give you the theta that you want. One thing I want you to notice is that if we solved for r, we can obtain negative numbers. Right? Because we have the r can be the plus or minus the square root of x squared plus y squared. And so now, because r is conceived of as a distance, what does it mean to have a negative distance? So here's what it means. If someone gives you a point in polar coordinates and the r coordinate is negative, what does that mean? doesn't need to be a negative distance. So here's the convention. Negative r means we move in the opposite direction of the angle. What does it mean by the direction of the angle? So let's actually talk about that. In the same way that when you have a negative x-coordinate on a number line, what does that really mean? Well, it means instead of moving to the right, you're going to move to the left. It's really a directional thing. In the same way, we will have directional meaning associated with the negative r. So if someone tells me, say, r comma theta is minus 2 comma pi over 4, what does that actually mean? Well, this is my xy plane. So here, I'm going to consider the circle of radius positive 2. So I'm going to think of there's a circle here of radius positive 2. I will locate the angle, pi over 4. Now if someone told me about 2 comma pi over 4, that would be this guy, 2 comma pi over 4. What does minus 2 comma pi over 4 means? Well, it means instead of going that way, literally going the opposite direction. That point is going to be the point minus 2 comma pi over 4. Okay? So negative r just means going the opposite direction of the angle. So instead of going towards the pi over 4 angle, we'll actually go in the opposite direction, which technically is going to be the 5 pi over 4 angle. Now, that brings up another point. This is in fact equivalent to saying 2 comma 5 pi over 4. And it turns out that is equivalent to saying a bunch of other things. This leads to another peculiarity of the polar coordinate system. There is no unique way to locate a point. In the rectangular coordinate system, there is a unique way to locate any point. In the polar coordinate system, there isn't. This also And this is because of how angles work. You can move around and go, for example, if I give you a coordinate r comma theta, you should realize that that is going to be equal to r comma theta plus any integer multiple of pi, right? I can just keep adding 2 pi. What you'll do is you'll go all the way around the circle and come right back where you started. So I can change the number in the second coordinate, and it will give me the same location, but in a different representation. You can also notice that what I can do is also take the negative of this guy and actually just add an odd multiple of 2n plus 1 over 2 pi. Right? So I can go to this angle, add pi to it, and that's going to give me the other angle, and etc. Now at this point you might be thinking that this coordinate system is more trouble than it's worth. Now, I don't know, you can give me different addresses for the same point. What kind of crap system is this? Well, it's still very important. We'll get to it. Okay, so that's important. Polar coordinate system is locating a point based on an angle and a distance from the origin. Negative distance means go in the opposite direction of the angle, as well as, because we are using angles, 2 pi brings us to the same point. as well as changing the angle by pi and making the coordinate negative will give us the same location as well. Despite all this, it's very convenient to learn how to operate in this new coordinate system. Let's get ourselves familiar with this new coordinate system. What else do I want to talk about at this point? Well, I gave some examples here. Do I need... That shouldn't be over 2, that should be an odd number. 20 plus 1. N is the integer. Let's do some examples here. Silly examples, but it's just for us to get used to it. Change to the rectangular coordinate system. R comma theta equals 2 comma pi. B R comma theta equals radical 3 comma pi over 6. Delta 2. Change to polar coordinates. The coordinate 1 comma 1, B. The coordinate 0 comma 2. Okay, 1A. Okay, how do we change that location into rectangular coordinates? Go. Yeah?
2 times cosine phi, comma 2 times sine phi.
Right, so x is going to be r cosine theta, that's going to be 2 times cosine of pi. Your y is going to be r sine theta, that is going to be 2 times the sine of pi. Cosine of pi, -1. Sine of pi, 0. So this means that my xy coordinate is going to be -2 comma 0. So that location is -2 comma 0. Actually just that. One B. Okay. I'll say didn't need 2 examples for this, but whatever. So this means your x is going to be r cosine theta. This is going to be radical 3 cosine pi over 6. Y is equal to r sine theta. It's going to be radical 3 sine pi over 6. Cosine pi over 6.
Root 3 over 2.
Sine of pi over 6. So this means, as I mentioned, you're going to need to be very good at your trig, like from now on. Also before, but especially from now on. So that would be the location. And so that's going to be 3 over 2. Radical 3 over 2 is going to be this point. If we want to switch from polar to, from rectangular to polar, to A. If xy is equal to 1, 1, how do I find the rectangular coordinates?
X squared plus y squared is r squared.
Right, so x squared plus y squared equals r squared. This means that 2 is equal to r squared. This means that r is equal to plus or minus radical 2. What about the other one, the angle?
Tangent theta equals y.
Tangent theta equals y over x, which means it's 1, which means our theta is going to be, can be pi over 4. Can also be plus 2 n pi. In fact, n pi, right? Because all students take. Right? The tangent is going to give you the same sign along that entire line.
It's A, it's TC.
Huh?
What are those letters?
All students take calculus. It's for you to remember which trig functions are positive and negative in which quadrant. All trig functions give you positive outputs here. Only the sine and hence the cosecant gives you positive outputs here. Tangent and cotangent gives you positive outputs here, and cosine gives you positive outputs here as well as secant. And all other trig functions are negative except the negative ones here. That being said, so for example, so our theta coordinates for this particular one, I could do something like radical 2 comma pi over 4. Or I could do minus radical 2 and instead add pi to pi over 4, which will give me 5 pi over 4. That's actually going to locate the same point, etc. There'll be an infinite number of ways to actually do this. In either case, what you can realize is that I would be on the circle of radius radical 2, and I can either look at the angle, pi over 4, and extend along that angle until I hit the circle. Or I could go to an angle 5 pi over 4, and then flip and go in the opposite direction, and so I make the r negative, and that's actually the same location. Yeah.
For questions like these, do you want us to just leave it at like r equals theta equals, or do you want us to give an example of?
Give a coordinate, because it will not be true if you mix and match the wrong things.
Okay.
Because if you were to put the positive radical 2 with the 5 pi over 4, that'll give you this point down here.
Okay.
So you should actually know that you'd have to pair, give me an example of a pair at least. So polar coordinates a little bit sketchy in the fact that there's an infinite number of ways to talk about any one location, and so you kind of have to be careful in locating things. But the benefits outweigh the risks overall. Let's also talk about, and this is starting, it's going to start to show you the benefits. Let's talk about sketching in polar coordinates. So we're going to start with some very basic sketches, and then I'm going to teach you how to do some more complicated sketches. Let's say you want to sketch r equals 1. Let's say you wanted to sketch theta equals pi over 4. Let's say you wanted to sketch r equals 2 cosine theta. Let's say you wanted to sketch r equals secant theta. Okay, so here's some examples of curves. Let's actually draw their pictures. Okay. We'll just kind of jump in here and kind of figure things out as we go. It's kind of hard to write down a general list of rules for how to graph things here. So, in our rectangular coordinate system, what would the picture look like if I were to draw a polar graph, as we would call it? What would the graph r equals 1 look like? Yeah?
A circle with radius 1.
That's it. It's a circle with radius 1. That's it, right? R by our definition represents the distance from the origin. So basically me telling you r equals 1 is like me telling you I care about all points that are distance 1 from the origin. This is in fact the unit circle. That already kind of hints to you why the polar coordinate system might start to become useful. Because what would the equation of the unit circle be in rectangular coordinates? X squared plus y squared equals 1. Now, the first thing you'll notice about that is that's not even a function, right? We have two outputs for each input. If I wanted to solve for one of these guys, I would get a plus or minus radical, right? Kind of annoying to deal with. In the polar coordinates universe, though, that's a constant function. In this universe, it's a line. In the rectangular universe, it's a circle with a complicated equation. So I can move from a situation where I have to deal with some complicated radical to a situation where I'm dealing with a constant. Right? So this is already kind of showing you how things can be simplified, right? A constant here is a circle over there. So in my r theta universe, if I'm plotting the r versus the theta, this is just a line. Translated to the rectangular coordinate universe, it's a circle. And already things are more complicated. This is another constant, but this constant is defined in terms of the angle. What does that mean? What would this picture look like?
Is it just a line with slope y?
It's a line. Now this says the theta is always at an angle of pi over 4. We define the angle to be the distance made with the positive x-axis. So I would just find the angle pi over 4, and I want all points that are lying along that line. For both, the positive r's will give me all the points along this ray, the negative r's will give me all the points along that ray. So in our rectangular coordinate system, this is the line y equals x. Now that's also not a very complicated function, but it's still more complicated than that. That is just a constant line, which is a line with slope 0 in the polar coordinate universe. This one is a line with slope 1, but it's already a different thing. What if I had r equals cosine theta, 2 cosine theta? What do you think that would look like? So here's a trick. We can use the actual equations to figure out a nice form for this. Notice what I would have is I can multiply both sides by r. What is r squared? Well, that's x squared plus y squared. What is r cosine theta? Well, that's just x. So in fact what this is, it's x squared minus 2x plus y squared equals 0. I can complete the square on the x. So that's actually this function. This equation in polar coordinates is this equation in rectangular coordinates. Nasty equation, but the cosine equation is actually pretty easy. What you would therefore have is a circle centered at 1, 0 with radius 1. So you have here a shifted circle, that should be a circle. Yeah.
Isn't the center 2?
The what?
Shouldn't it be 2, because x minus 1 is his square, wouldn't it be?
No, the general equation of a circle is x minus h squared plus y minus k squared equals r squared, where the center is going to be h comma k and the radius is r.
Oh, sorry, I was thinking about 2x.
Yeah, but you have to write it, the x is not in very nice form. So what I did is I completed the square here by adding 1 on both sides. X squared minus 2x plus 1 will give me the x minus 1 all squared. The y squared is just the same, and I'd add 1 on this side. So I did this by completing the square. Complete the square for So this equation, 2 times cosine, in the r theta universe, well that's not cosine, that's a sine. In the r theta universe, it's just a graph that looks like this. In the xy universe, it's a graph that looks like that. Okay, what about r equals secant theta? What would that picture look like? Let's see if we're getting how this thing actually works out. What kind of graph is that? What would r equals secant theta look like?
We're changing it to 1 over, sorry.
Yeah, go.
Can you do 1 over cos theta
Yeah, this is 1 over cos theta, okay?
and multiply cos theta to r, get x equals 1.
R cosine theta equals 1. So this means that x equals 1. This is the equation of a vertical line. X equals 1. So these two especially can actually show you why switching to this new coordinate system might be useful. We can go from ugly equations, all equations are beautiful, but you know what I mean, ones that are harder to deal with algebraically to ones that are easier to deal with algebraically. Let's look at some more complicated graphs though. To graph more complicated functions. By that I mean polar functions. It would help to graph them in the polar universe first. Then translate. So, for example, let's look at let's look at r equals sine of 2 theta. So we're going to figure out how to draw this. So now you might start out by trying, maybe I can do a little algebraic trick to manipulate this to look like one of our previous equations. So yes, you remember trig identity for sine 2 theta, that's going to be 2 sine theta cosine theta. Okay, but I don't have any r's, so you can multiply through by an r, so one of them will get an r, like the r cosine theta. So then, okay, multiply through by r again, so you have the r cosine theta and the r sine theta on one side, times 2, so that's just 2xy, that the other side. But now you'd realize on this side you have an r cubed. And that's going to be something that you have to expand and regroup, and it can become quite annoying pretty quickly. Then you can realize, oh, someone could put a 3 theta here, or a 5 theta, and now you're going to go down this trig identities rabbit hole that it's going to be hard for you to get out of. So there are other ways. Sometimes it actually helps to first graph it in the polar universe. So hopefully you remember your trig and what it means to graph sine 2 theta. Probably I should talk about that a little bit first. Okay, so to graph y equals a sine k x minus b plus c, or y equals a cosine k x minus b plus c. One thing you'll realize is that the absolute value of a will give you something called the amplitude of the graph. That's how far up and down you rise from the base level B is going to give you what's called the phase shift of your graph. Phase shift because of the language used in physics and differential equations, but it's just a fancy name for horizontal shift. C is going to be the vertical shift of your graph. What does the k tell you? Well, if you take 2 pi and divide it by k, absolute values if it's negative, this will give you the period of the graph. And the period divided by 4 is a useful graphing subinterval, because what you'd realize is that sine and cosine comes in 4 sections really. Right, so if you think of y equals sine of x, yes, you ordinarily think of the graph looking like this for one period. But the thing is, you can actually box this guy in a rectangle, and there are 4 distinct phases to the graph. There's a point where you go from the lowest point to the highest point to the middle point to the lowest point, the lowest point to the middle point, right? Also, sine also comes in 4 sections, because of course, after all, a sine is just a shifted cosine or vice versa. That would be the cosine graph. You can also bound this into 4 sections. These are the distinct phases. So there's a point where you go from the highest point to the middle point to the lowest point to the middle point to the highest. Okay? So if you can figure out this entire length here is called the period. This is the pattern that repeats forever. Right? So once you can figure out that length, that's going to be given by 2 pi over k. The period over 4 tells you what's the length of each of these subintervals, and then based on whether you have a sine or cosine, you know how to plot points within those subintervals. That's going to help you actually sketch the graph in the r theta universe. So here, the vertical is going to be your r, and theta is going to be the input that you're plugging in. So let's actually look at r sine 2 theta. What would that graph look like? So if I have r equals sine 2 theta, the first thing I'm going to realize is that just means the amplitude is 1, the phase shift. Oh, let me draw a generalized graph here. How do all these numbers actually come up? So let's say this is your x, y, theta versus r. Okay, so the c, the vertical shift, that's usually the guy you want to put in first. So let's say that's just some number, some positive number. This is your c. I would tend to want to put that in first. Okay? Now the amplitude, the a, this is how high up and how low you would go from that c. So you move up a distance of a, so this distance here is going to be a, and then you move down a distance of a. So that is the highest point, this is the lowest level. So I probably put in the a second. Then the b tells you how far you're shifted horizontally from the origin, so let's say your b is just some positive number. Let's say it starts here, I'd probably put in that number first, third. So the b is the line that starts here. And then from there what you do is you just tack on 4 sections. And the length of each of these sections is going to be the period over 4. So once you know what this coordinate is, you can figure out all other coordinates based on that coordinate. And depending on what you're graphing, let's say just for argument's sake, you're graphing a y equals a sine k x minus b plus c, where your a is, say, a negative number. What that means is you should draw a graph that looks like a negative sine graph, which means you're going to take the sine graph, you're going to flip it upside down. So that's going to tell you, you would go from the middle point, but instead of going up, you will go down. then you'll go back up to the middle, then you'll go to the top, then you'll go back down here. So the graph actually would look like this. Right? So this is a very quick crash course in how to sketch sines and cosines from pre-calc class. Okay, so now that we know that, we need to know that very well because we're going to need to be able to sketch this thing very quickly because that's not the graph we care about. We care about the graph in the xy universe, not in the r theta universe. This graph is just to help you sketch the other graph. So you're going to want to be able to do this very quickly. It's kind of a really efficient way of plotting points, as you will see. So instead of doing a table of values, we're going to be graphing trig functions to help us graph other things. Okay. Now let's look at r equals sine 2 theta. First of all, I'm going to notice that that means the a is 1, the b is 0, the c is 0, my k is 2. That is going to tell me that the period is going to be 2 pi over 2, which is pi. Then the period over 4 is just going to be pi over 4. So I'm going to start to sketch this in the r theta universe. And I am going to want to sketch between 0 and 2 pi anyway, just to get a full revolution, get the full picture of what this thing is doing. But yeah, so my c is at level 0, so that's just the regular, that's just the axis, the horizontal axis here. My b is at level 0, so I'm not moving to the left or right, so that starts here. My amplitude is 1, so I'm going to go up to a level 1, I'm going to go down to a level -1, and then I'm going to put in a skeleton here. I know I'm going to slice this into now, the period is pi. So I have a full sine graph happening in this. So I'm going to split that into 4. Then there's going to be another copy in the next one. So I'm going to split that into 4. Now, that's just a positive sine graph, so I know the pattern. The pattern is, it will start at the origin. It will then go up, then the middle, go down, then the middle, then go up, then the middle, go down, then the middle. So that's what it's doing in the r theta universe. Now what we're going to do is we're going to translate this into the xy universe. So here's how that's going to happen. All the important numbers that show up on the vertical axis, you're going to sketch very faintly a circle of that radius. You're going to take the absolute values of all these numbers here. So the center line is 0, the highest line is 1, the lowest line is -1. Take the absolute values of all those numbers, you want circles of those radii. And so the circle of radius 1 is the only one that's applicable here. It's not a part of the graph, so you draw it in broken lines very faintly, because it is just telling you this is the maximum distance you're going to extend from the origin. The next thing you're going to want to do is you're going to want to fill in all these angles. So we know that the period over 4 is pi over 4, so this here is going to be at pi over 4, this here will be at 2 pi over 4, this here will be at 3 pi over 4, this here will be at 4 pi over 4, this here will be at 5 pi over 4, this will be at 6 pi over 4, this will be at 7 pi over 4, and this will be at 8 pi over 4. You're going to want to sketch all the angles that appear. So, we're going to have the angle of pi over 4. We're going to have the angle of 2 pi over 4. We're going to have the angle of 3 pi over 4. We're going to have the angle of 4 pi over 4. We're going to have the angle of 5 pi over 4. We're going to have the angle of 6 pi over 4. We're going to have the angle of 7 pi over 4. And we're going to have the angle of 0, which is equivalent to my 2 pi. Okay. So here is how we're going to get the graph. We are going to use the r and theta coordinates from this graph. So, in the beginning, when theta is 0, notice that my location is also 0 units from the origin. So the graph starts out at the origin. Now what's going to happen is as my angle increases to pi over 4, my distance from the origin is going to increase to 1. So I'm going to go from the situation where I'm 0 units from the origin to the situation where I'm 1 unit from the origin once I'm on the angle of pi over 4. So that's this first arc right here. Now where do I go? Well, the r coordinate changes from 1 to 0 as I move from the angle pi over 4 to pi over 2. So, as the angle increases from pi over 4 to pi over 2, my distance from the origin is going to decrease from 1 back to 0. So I get that, which is often called a leaf for obvious reasons. So now I'm here. Now what I'm going to do is I'm going to move to the theta, which is 3 pi over 4, which is this angle here, but my r value is going to be minus 1. What does that mean? So here, to go into the direction of 3 pi over 4 is that, but my r is negative, which means I'm literally going to go the opposite way. So I'm going to go down to hit this point, the opposite direction of 3 pi over 4. That's when I'm here. Then I'm going to go back, once I hit the angle pi, I'm going to be back at a distance of 0, so that's going to come around and then boom, I'm back at the origin. Now we're here. So we remember we're on the angle pi. Now I'm going to move to 5 pi over 4 and jump on the circle of radius 1. Boom. Now I'm going to move to the angle of 3 pi over 2 and go back to the distance 0. Boom. Now I'm going to move to the angle of 7 pi over 4, which is over here. However, my r value is a negative 1, which means I'm going in the opposite direction of 7 pi over 4. Boom. And then once I come back to 2 pi, I'm at a distance 0 from the origin. Boom. So this is the polar graph. It's a 4-petal flower thingy. There's a technical name for it, but I never remember it. So that would be what the polar graph is. So you want to sketch a flower, that's an equation. Come up with this equation in rectangular coordinates. It's not going to be very nice to write down, much less to have someone sketch it. Like you can, as well as you'll notice that it's not even a function, it doesn't pass the vertical line test. There are going to be times where any particular x value is going to give you like 4 y values. So if you really want to be mean to your pre-calc class, you can just give them that graph to sketch, but give them in rectangular coordinates instead. Okay, figure out what this graph looks like by plotting points, and they'll spend the rest of the semester trying to figure that out, actually. You know how many points you have to plot to figure out that that's the graph? You plot 1 point, it's over here. Plot another one, it's right here. Plot another one, down here. Plot another one, up there. They'll just have like a mass of points all over the place. I don't know what this is. Plot some more points, kid. You'll have to plot a lot of points to figure out that graph. So that's not very efficient. It's much more efficient to first sketch the normal trig graph, then use the points here to figure out what it would look like in that universe. So I have a very complicated function here in the xy universe. However, in the r theta universe, that's just sine 2 theta. I can deal with that guy easy. To do calculus with that guy, come on, it's gonna be a nightmare. Let's sketch some more. So there are times when I'm going to ask you to sketch a graph, and I'm going to ask you things like, what is the area of one of these petals? Or things like that. Or what is the distance traveled as I move along some arc? Things of that nature is what we're going to want to be able to answer. But in the meantime, let's actually sketch some more pictures. Now we won't get through all of these, but I actually want you guys to try one. Well, the first one is 2 cosine 3 theta. But that's actually super similar to this one in terms of ideas. So probably what I'd rather you do is graph B first. What does that graph look like? So sketch B. Give you guys 5 minutes. So you know how to draw pictures, we will soon be doing calculus with polar coordinates. One more minute. Anyone actually started this picture yet?
Yeah. I think so. Is it just like
definitely try to sketch the others before next class, that way you'll know what you get and what you don't get about this process. Hopefully you tried it now, so you'll kind of understand where you're stuck and what needs to be worked on. Let's do B first, so we'll do the others next time. Okay, what's the first thing you did? How do we figure out what that is?
-2, you could rewrite it as like -2 times theta plus 3. Or yeah.
Yeah?
And the k is 1, so the period's 2 pi.
Okay, is 1. What about the others? So the absolute value of A is what you care about, that's 2. Your B?
3. No. 0.
0. Because there's no
There's
translation in
nothing,
the
yeah.
angle. Your C?
3.
C is 3. Your K is 1. Once you identify all the letters, you can start to find all these guys, so you know that the period is 2 pi over K, so that's just 2 pi as usual. Your period over 4 is going to be pi over 2. And now you can start to graph those guys. So what's the first thing you put in here? You put in the 3. So that is our new baseline. So what do we do with that? What's the next thing you put in?
So you can put in 5 and 0.
You move up by 2 and down by 2, which brings us to
1.
1. So that's the highest point and the lowest point. I know my B is 0, so that's the left, the axis is the first starting point, but I'm going to throw in 4 sections off that, and I know the last section is going to end at 2 pi, because that is the period. The period over 4 is going to be pi over 2, so I know that this is at pi over 2, that's at 2 pi over 2, this is at 3 pi over 2. And this here, what is this graph going to look like now?
It goes down first.
Right, so it starts at the center, it's a sign, but it's a negative sign, so it's going to go down, then back up, and down. So that is the graph in the R theta universe. Let's figure out what the xy is going to look like. Okay, so what did you do here? What was the first thing you did?
A circle with radius
Was radius what?
2,
Why?
because that's the amplitude.
That's not what we used to draw the circles. The circles comes from these numbers here. We actually in fact need 3 circles for this picture. There's going to be a circle of radius 1. There's going to be a circle of radius 3. And there's going to be a circle of radius 5. Remember, the important thing is the R values. This is R. The highest point is located when R is 5. The middle point is located where R is 3. The lowest point is located where R is 1. I want to talk about R. 2 is not even on this picture. Right? I mean, there's a 2 here, but there's no, I don't know what those actual specific coordinates are. So you use the numbers on the y-axis. So that's very important. Know that. You use the numbers on the y-axis. So every number that shows up on the y from the important numbers that you have here, you're going to take the absolute values of each of those numbers. You need a circle for each of those numbers, because that tells you at some point I'm located at a distance from the origin. We can think of that as us being on a certain circle. So we're going to start with the beginning of our graph starts when theta is 0 and our location is 3 units away from the origin. So the first point starts here. That's where the graph is going to start. That is on an angle of 0. So that also tells us that we need some other, so the first thing you want to do is put in the circles. The second thing you want to do is put in the angles, but these angles are actually on the axes themselves. So this is 0, which is the 2 pi. Pi over 2 is going to be the other angle. Pi is going to be the other angle. 3 pi over 2 is going to be the other angle. And 2 pi. So we're going to start there. Now, as the angle increases to pi over 2, our distance from the origin decreases to 1. So I'm going to jump from the circle of radius 3 to the circle of radius 1 as the first move. Then, as my angle increases to pi, I jump back to the circle of radius 3. So this keeps going like that. So the first curve is just one arc going like that. Now as I move to 3 pi over 2, my distance from the origin increases to 5. So I'm going to jump to the circle of radius 5. And then I jump back to the circle of radius 3 when I'm at the angle 2 pi. So that looks, it's not quite like an egg, but it's just this like oval where you just stretch out the bottom of it. So that would be that graph. So it never actually hits the origin.
That's how I drew it.
But make sure to actually sketch the others, make sure you know how to figure that out,
I
because
don't know how to work it out.
we'll need the graphs to do what we're going to do